All right, let's dive right in. Today, we're going to look at the secret blueprint of our digital world. We're talking about the fundamental, hidden rules that control how information moves around, from your phone to the internet to, well, pretty much everywhere.
So, have you ever actually stopped to ask that question? I mean, how does information really work? Not the code, not the hardware, but the deep underlying principles, the absolute rock solid rules of the game. It's a question that gets to the very core of our modern world.
And believe me, this isn't just some abstract philosophical question. The answer is playing out all around us, right now. You see it in the incredible, complex dance of a whole formation of self-driving cars, all coordinating their movements. They're constantly sharing this critical stream of information to move safely and efficiently. You also see it every time you open up your social media feed. Ever wonder how a meme just explodes? Or how an idea seems to spread like wildfire through a network? Well, that's not random. It's information flow in action, and it follows these surprisingly predictable, deep-seated patterns. And if you zoom all the way out, it's what makes the entire internet hang together. Ideas like network coding, which is basically a super clever way to move data around, rely on these fundamental principles to make our global networks stronger, faster, and way more efficient. Okay, so here's the game plan for today. First, we're going to see just how pervasive information is. Then we'll uncover the secret blueprint for it. We'll peek inside the axiomatic toolkit it gives us, see how all that theory actually connects with reality, and then finally, we'll talk about why this blueprint is such a huge deal. So first up, information is everywhere. We see it in all these incredibly complex, totally different systems. But here's the million-dollar question. Are they all secretly playing by the exact same rulebook? Is there a single set of deep rules that governs all of them? Because, just looking at each of these systems one by one, that's not going to cut it. It's kind of like studying individual trees and never really understanding what a forest is. To get the big picture, you've got to go deeper. You need a fundamental theory. And that brings us right here to Section 2, the blueprint for information. This is where we get to uncover those universal rules of the game, the ones that apply to every system, everywhere. Now, the key to this whole thing is something called the axiomatic approach. I know, that sounds kind of heavy, right? But the idea itself is actually beautiful and simple. Just think back to geometry class. You start with a few simple truths you just know are true, like you can draw a straight line between any 2 points. Those are your axioms. And from just a handful of those basic rules, you can build the entire world of geometry. Well, this is the exact same idea, but for information. And this isn't just some new idea. This quote here is from the pioneering work by John Barwise and Jerry Sagelman. Their goal was nothing short of revolutionary, to create a theory of information flow from the ground up, to find that primitive logic for how any distributed system works. It was a total game changer. So, what do we actually get from this theory? What's inside the box? Well, let's open up the axiomatic toolkit and check out the core components that make this whole idea so powerful. Okay, so here's what we're working with. First, you have information channels. Pretty straightforward. Those are just the pathways the info flows through. Then you have local logics, which are the specific rules inside one part of a system. But here's where it gets really cool. Infomorphisms. Think of them as perfect translators. They let you map one local logic onto another without losing a single drop of information. And once you have that, you can build up to distributed logics to describe the entire network. And this whole toolkit is so robust, it can handle anything from simple on-off Boolean operations all the way to the mind-bending rules of quantum logic. And the sophisticated engine making all of this work, it's a field of math called category theory. Now, don't worry, there's not going to be a quiz. All you need to know is that this is the heavy-duty mathematical language that makes sure this whole structure is airtight and logically sound. Okay, enough theory. That's all great, but so what? How does this blueprint actually connect with the real world? Well, that's what we're going to look at now, how theory meets reality. So, imagine you're an engineer and you want to use this. The process is actually pretty clear. You start with your system. Let's say it's a simple control network that uses true-false logic. Then you apply the axiomatic principles, the rules from that toolkit we just looked at. And just by doing that, you can start to analyze its really deep core properties, like how stable it is or how much control you can have over it. And the whole reason for doing this, the big payoff, is that it gives engineers real, tangible insights. It helps them answer really tough questions, like what's the impact of a communication delay going to be? Or how do we design a better control system for this factory? It's not just an academic exercise, it solves real problems. When you boil it all down, this whole theory rests on one beautiful, elegant idea about two sides of the same coin. On one side, you've got uncertainty. That's just the state of not knowing. A whole range of things could be true. And on the other side, you've got information. And what is information? It's simply the reduction of uncertainty. The theory calls it a generalized constraint. Every piece of information you get is like a clue that eliminates some possibilities, narrowing things down and getting you closer to the truth. And that brings us to our final section, the big finish. Why does any of this matter? What's the ultimate takeaway from this whole powerful idea? It's this. This is what it's all been leading to, the axiomatic approach. It gives us a universal language. It's a single, powerful framework that can describe and predict how information is going to behave, whether you're talking about a living cell, a social network, or even a system for interstellar communication. It's like the universal grammar of data. So if you walk away with just a few things today, let it be these three. First, this gives us a universal rulebook for information flow. Second, it gives us a really solid formal way to understand and manage uncertainty. And third, and maybe most importantly, this is the foundation we need to build the bigger, better, and more stable digital systems of the future. Which leaves us with one final, pretty exciting thought to chew on. Now that we have it, this universal blueprint for information, this fundamental understanding of how it all works from the ground up, what are we going to build with it next?